So hello everybody, this is the second video about chapter 1 about divisors, prime numbers and GCD. So if you remember what I've told you in the first video, using a Euclidean division between two integers number a and b, there are two values, the quotient and the remainder. Sometimes, as the remainder is greater than or equal to 0 and less than b, sometimes r can be equal to 0. If r is equal to 0, then b divides a, or b is a divisor of a. We can write it down using the following little symbol as a vertical bar. B divides A. So why do I specifically speak about the fact that when the remainder is equal to 0, then B divides A? It's because this property is very important for integer numbers, and actually it will be the core of what we'll see later in the course. So when B divides A, then A is equal to B times Q plus 0. Okay, now what about the properties of divisor for integers number? So let n be an integer number. We will suppose that n is a positive number. That's not very important, but in all the examples in the course later, we will always use positive numbers. So let n be an integer numbers. Let's say that we divide n by 1. Then the quotient is n and the remainder is 0, independently of the value of n. So for all n integer number, 1 divides n. So let's do another quite simple Euclidean division. N divided by n, the quotient is 1, and the remainder is also 0. So as a remainder is 0, this means that n divides n, and that's true for any value of n. So for any integer number, n has at least two divisors. N may have more than two divisors, but it has at least two divisors. So we can kind of sort numbers by this property, because some numbers only have two divisors. One and actually themselves, because any number has one and itself as a divisors. And some numbers, all the others actually, have more than two divisors. So the number that only have two divisors, perhaps you know about them, they are called prime numbers. Prime numbers actually have only one and themselves as divisors. The others are no specific names. So the prime numbers are very important regarding also what we'll talk about in future videos, and actually in all the chapters you'll see later. So you probably know a list of prime numbers. For example, 1 is not a prime number. So let's take it apart immediately, because 1 has only one divisor. Okay, so 1 is not a prime number. Prime numbers, classical, quite of I call classical lists. 2, 3, 5, 7, 11, 13, 17, 19, 23, and so on. So all those prime numbers you should know by now. For the other numbers, actually we can try to check and know what are their divisors. So how to find the divisors of a number. This task is quite easy. The number is not too high. Let's say for numbers inferior to 1000, you can try to find the divisors. As long as the number increases, it's very hard to do, and if the number is a very huge number, it's nearly impossible to find its divisors if the number has a few number of divisors. I'll talk about this later about RSA, the RSA crypto system, when the fact that finding the divisors of a number is not an easy task, and fortunately it's not an easy task. So to find the divisors of a number, you can try to make the Euclidean division using some numbers. For example, let's take at random the number 138. Actually, we can see that this number is a multiple of 2 because it ends by 8. So it's 2 times 69. 69, as you can see, it's a common property of numbers that the sum of 6 and 9 is 15, which is a multiple of 3. So 69 is a multiple of 3. It's equal to 2 times 3 times 23. And as you can see, I can't go on further because 2 is a prime number, so I can find any divisor to go on. 3 is a prime number also, so I can find another divisor. And 23 is also a prime number. So you see that those numbers 2, 3, and 23 are part of the list of prime numbers. So here I know that 138 is 2 times 3 times 23. Now all the divisors are combinations of those numbers. So for example, 1 is a divisor of 138. 138 is a divisor of 138. Then 2, 3, 23, and combinations of its divisor are also divisors. Let's say that, for example, 2 and 3 are divisors. So 6, which is 2 times 3, is also a divisor. 2 times 23 is 46, is also a divisor. And 3 times 23 is 69, is also a divisor of 138. So we have here the list of all the divisors of 138. And what you can see is that in order to find this list, the easiest way to do is trying to make a decomposition of my number, here 138, as a product of prime numbers. So from this example, I can now talk about the fundamental theorem, of arithmetics. From this example, actually, this will be true for any integer numbers. So for all n as an integer number, n can be written or decomposed as a product of powers of prime numbers. So let's highlight this, again in red. Whatever the number you consider, you can write it as a product of powers of prime numbers. Let's take simple number. For example, 4 is 2 times 2 is 2 squared. 10 is 2 times 5, which are both prime numbers. 98 is 2 times 49 is 2 times 7 times 7 is 2 times 7 squared. So you can try by yourself with any number that you choose. You will always end as a number expressed as a product of powers of prime numbers. So from those products of powers of prime numbers, we can do exactly the same thing that we've done previously with the example of 138, that is finding all its divisors. Okay, so what's next about that is, the GCD. The GCD is the greatest common divisor of two integers. Actually, one can compute the GCD of more than two integers, but at the moment that we understand how to do with two integers, it's quite easy to do with any number of integers. So let's take two integer numbers, A as a list or set of divisors. Remind that this set can be composed of only two values if A is a prime number, but it can have any number of divisors. B also has a set of divisors. So the GCD, actually, if you just read the name, you can quite understand what is a GCD. It's the greatest common divisor. So the GCD D of A and B is the greatest value such that D is a divisor of A and D is also a divisor of B. I think that's quite easy to understand. Now the problem of the challenge is how to find D from A and B. So actually, if we have the full set of the divisors of A and the full set of the divisors of B, we can try to sort them in ascending order, compare the list, and try to find which one is in common in this list. So, for example, let's take A equal to 138. Then the list of all its divisors is known: 1, 2, 3, 6, 23, 46, 69, 138. Okay, let's take, for example, B equal to 21. Actually, 21 is equal to 3 times 7. That's how we can decompose B21 as a product of prime numbers. So the divisors of 21 are 1, 3, 7, and 21. Actually, we just have to look through both the list, and we see that the element which is common to this list and which is the greatest here is 3. So here the GCD of 21 and 138 is equal to 3. It's the greatest common divisor of those two numbers. So this is possible to do, but actually, when the numbers are becoming bigger and bigger, it might be hard to find the whole set of divisors, and actually even too hard for a computer to do. So in order to have a method which is efficient at computing the GCD of two numbers, one can use Euclid's algorithm, which is a fast and efficient way of calculating or computing the GCD of two values. And actually, this algorithm is only based on Euclidean division using the remainder. So how to proceed? For example, from A and B, which are both integer numbers, and let's assume that A is greater than or equal to B, then Euclid's algorithm is simply building a little table with 3 columns. The first one with a value of A, the second one with a value of B, and the third one with the value of R. So I don't know for the moment, depending on the value that will be chosen, how many lines will be necessary to find the value of the GCD using this algorithm. So the purpose is here to, as a sequence, so let's act as a little computer program. One, initialize the A column with the value of A. Then initialize the B column with the value of B. So number A, number B. Then compute R with an Euclidean division. Actually, the name of the column is really the remainder of the Euclidean division of A by B. Second part of the algorithm, it is a sequence used to make the calculation. And this is quite of algorithmics. If R is different from 0, then for the following lines, the A column takes the value of the B column above. So this is a little green arrow. The B column takes the value of the R column above. So here B, R, and now compute the remainder, of the Euclidean division of B by R. You will have a new value, which is a new remainder, and jump back to step 2. If R1 is different from 0, then go ahead and put in the A column the value which is in the B column above, and in the B column the value which is in the R column above. So that's all for the second video. I'll make a short video as an example and illustration of the Euclid's algorithms on real values.